Hello everyone, I'm Mary Swarna, working as an assistant professor in the Department of Electronics and Communication Engineering. In today's lecture, we are going to discuss the topics of the stationarity and the statistical independence of a random process. In the previous lecture, already we have seen the definition of random process, and then we have explained the concept of random process into classification. So what is a random process? A random process is a function of both the time variable as well as the outcome of the experiment, yes. Or else you can define the random process as it is a combination of all the time functions. And for each and every outcome of the experiment, a time function has been assigned, and the combination of all these time functions is called as what? Random process. And we have classified the random process into 4 types like continuous random process, discrete random process, continuous random sequence, and discrete random sequence. In today's lecture, we are going to see the topics on stationarity of a random process. How can you say that a random process is stationary or not? And similarly, how can you say that 2 random processes are statistically independent? So, the definition of the random process which is stationary. So, how can you say that a random process is stationary? The definition is a random process is said to be stationary if all its statistical properties does not change with time. Here, what is a random process? It is a function of both the outcome of the experiment as well as the time. So, there is nothing but you can simply represent it by x of t. So, with respect to the outcome, you are going to calculate what? Statistical properties. So, with respect to the outcome of the experiment, you are going to analyze the random process, the statistical properties like mean, variance, correlation, and all those things are called as what? The statistical properties. Statistical average or mean. And similarly, you can calculate with respect to the time, then they are called as what? The time characteristics. Or it is called as what? Time average of the random process. So like that, you can calculate the time autocorrelation of the random process, time cross correlation of the random process. It means with respect to the outcome of the experiment, we are going to study the statistical characteristics. With respect to the time variable, we are going to study the time characteristics like average, correlation, time autocorrelation, time cross correlation, time covariance. So, all these properties are going to analyze. So, first we will see with respect to the outcome of the experiment like statistical properties. Therefore, what is a stationary random process then? A random process is said to be stationary if all its statistical properties. So, what do you mean statistical properties here? It may be mean, or it may be variance, or it may be mean square value, correlation, covariance. All these are called as what? Statistical properties. So, the statistical average of any process can be denoted by E of. And similarly, the time average, if you want to calculate, that can be represented by E of. So, these are the usual notations to represent the statistical averages and to represent the time averages. Now, if the random process is stationary, then their marginal and the joint density function and the corresponding distribution function will not vary with time. If the time changes, then the corresponding distribution function and density function of the random process will not change. If they are not changed, means their statistical properties will also not change. Then the random process is to be what? Stationary random process. Okay. Now, we are considering a random process x of t. Now, we have taken if the time is fixed. What is a random process here? Random process is a function of both the sample space element or the outcome of the experiment as well as the time. So, we have taken 3 cases. If the outcome of the experiment is fixed, if the time is fixed, if both are fixed, we have taken 3 cases. In the first case, if the time is fixed. If the time is fixed, then the random process is called as what? Random variable. If the time is fixed, then the random process, this x of s comma t simply can represent by x of t. Then this random process is considered as a random variable. If you fix one of the variable, which variable you are going to fix? If you fix a time variable, then this random process is a function of what? If t is fixed, it is constant here. So this is constant. If this constant is not varying, it is varying only the variable s. If it is varying only the variable x, it is called as what? Random variable. Therefore, if the time is fixed in the random process, then the random process is corresponding to the random variable. That's why here also consider a random process x of t with random variables. Now, for example, if I fix at t equals to t1, I'm fixing here t equals to t1. Then what is x of t1 is equals to x of s comma t1. It's nothing but x1. This is a one random variable. And similarly, if you fix a time at t equals to t2, then you'll get x of t2 is nothing but x2. So this is another random variable. So like that. So what is the random process here? X of t, the random variable here, x of ti. Then what is x of ti is equals to xi, where I equals to what? 1, 2, 3 and so on, n. So if I equals to 1, then what do you get here? X of t1. My time is here t1. Then what is x of t1 is equals to x1. If I equals to 2, then what is my t equals to here? t2. Then here x of t2. What is x of t2 is nothing but x2. So x of ti is equals to xi. Where what is I value here? 1, 2, 3 and so on up to n. Because for this random process, you are considering n random variables. That's why you have to fix a time t at n number of time instance like t1, t2, t3 and so on tn. Now, these n random variables of this random process x of t is having the joint probability density function. So, fx of x1, x2 and so on xn comma t1, t2 and so on tn. So, then this process is said to be what? Stationary. When can you say that this process is stationary x of t? If its density function, so it is called here joint density function because it is involving more than one random variable. Therefore, it is called as what? Joint density function. So, if this joint density function is not varying with a time. If here previously at t1, what is my random variable here? x1. So, at t equals to t1 plus tau, again, the random variable here is nothing but here x1 only. So, it means if time is varying, the joint density function is not varying. If the joint density function is not varying means all the statistical properties like the mean, variances, all those are constants. So, that's why here the definition is if the joint density function or the density functions of the random process is not varying with a changing time, with a shifting time, then you can say that the random process is stationary. If the random process is stationary, then all statistical properties like mean, variances, correlation, all those things will not change with time. They don't depend upon the time variable. And what is the definition of a non-stationary random process? So here a random process to be stationary if statistical properties does not change with time. And what is non-stationary random process? If the statistical properties changes with the time. So if they changes with the time, then what about the joint density function will also changes with time. If t1 is changing from t1 plus tau, then the density function value is changing. So the joint density function is also changing with time. If they are changing with time, then the corresponding statistical properties will also change with time. Then the type of random process is called as what? Non-stationary random process. So if they are changing with time, then whatever the statistical properties I told, here they don't depend upon time, but here they depend upon time. So if you calculate the mean, variance and all those things, so you'll get in terms of t. Okay, so that is a definition of stationary random process and non-stationary random process. Okay, so after that we are going for first order density functions of a random process. In the previous lecture already we have seen the distribution function, density functions of a random process like first order distribution density function, second order and third order like that. We have seen up to nth order distribution density function of random process x of t. Okay, what is here x of t is my random process. Now if x is a random variable, Then what is this distribution function? Fx of x is equals to what? P of x is less than or equals to x. And what is the corresponding density function? D fx of x by dx. So these are the distribution functions and density functions of a random variable x. This is I'm telling with respect to the random variable x. Now what I'm taking here, I'm taking a random process x of t. Now how can you write down this distribution density function for this random process? For that, what you have to do? You have to fix the times. You have to fix the time. Then you can convert that random process into what? Random variable. So if the time is fixed in the random process x of t, then the random process can be considered as a random variable. So for example, at t equals to t1, then what is x of t1 is equals to x1, it is a random variable. So at t equals to t2, x of t2, nothing but x2, it is also another random variable. It means for a random process x of t, if you are fixing the time slots for n times, then you are getting the n random variables like x1, x2 and so on, xn. Now what is the first order density function? It means I am fixing the random process only at t equals to t1 or only at t equals to t2. Only at one time slot I am fixing the random process. Then the corresponding distribution function is called as what? The distribution function, the first order distribution function of the random process x of t. Here fx, what is x in here? It is a random process. Here what is x indicates a random variable. So this is a distribution function, the first order distribution function of random process x of t for a specific t value. So what is that? P of x of t is less than or equals to x. For example, if I fix at t equals to t1, then how can I write the first order distribution function of the random process x of t as fx of x1 comma t1? Because if t equals to t1, then what is x of t1 is equals to x1. Therefore, fx of x1 comma t1 is equals to what? P of x of t1 less than or equals to x1. So here what is the distribution function here? X is less than or equals to x. With respect to the random process, x of t is less than or equals to x. If t equals to t1, then what is this random process? So it is becoming what? Random variable x1. So in place of x of t1, I can replace by x1 here. Then what is fx of x1 comma t1 is equals to p of x of t1 less than or equals to x1. So like that, what is fx of at t equals to t2? So at t equals to t2, what is the distribution function? Fx of x2 comma t2 is equals to what? P of x of 2 less than or equals to x2. So like that, it is called as what? The first order distribution function, because it is defining only with one random variable. That's why only either t1 or t2 or t3 and so on at tn. So this is called as what? First order distribution function. And if you know the distribution function, how do you calculate the density function? What is the relation between these two? The differentiation of the distribution function gives the density function. And similarly here also, the same concept I am applying to the random process also. Because random process is equals to a random variable if I fix the variable type. That's why whatever the properties applied and the definitions applied for random variable, the same definitions and the same properties will also be applied to the random process if I fix the variable time t. Now what is the density function here? Fx of the density function the random process, fx of x at t equals to, so t may be anything here. It may be t1 or it may be t2 or it may be t3 or it may be and so on tn. Then what is in general fx of x comma t is equals to dou fx of x comma t by dou x, or else it is also called as, since it is involving only with one variable, in place of partial differentiation I can take the differentiation also. So d fx of x comma t by dx. So d fx of x comma t by dx. Now I am taking here t equals to t1. Then what is the density function? The first order density function. So if t equals to t1, then what is x of t1 is equals to x1. Therefore, this is called as what? x1 for what value of t? If t equals to t1. So fx of x1 comma t1 is equals to what? D fx of, see here, d fx of at t equals to t1 can represent by what? Fx of x1 comma t1. So x1 comma t1. If t equals to t1, it becomes what? x1. So x1 comma t1 by d at t equals to t1. X is becoming x1 here, the random variable x1. So x1. So this is the first order density function of the random process x of t. If you want, you can write for at t equals to t2 for the random variable x2 also. So these are called as what? The first order distribution function and density function of the random process x of t. Next, I am taking 2 time slots t equals to t1 and t equals to t2 for the random process x of t. So I am fixing 2 slots t equals to t1 and t equals to t2. And if I fix t equals to t1, then the random process is becoming what? The random variable here that can be represented by the variable x1. At t equals to t2, this is nothing but what? The random variable x2. Then I want to calculate the joint distribution function of these 2 random variables. In the previous case, I have taken the distribution function individually. The distribution function of the random variable x1, and similarly the distribution function of the random variable x2, and so on, the distribution function of the random variable xn. But here what I am taking is the joint distribution function of the 2 random variables x1 and x2. Then it is called as what? Second order, because I am taking 2 random variables. So it is called as what? Second order joint distribution function. Then how it is given by fx of x1 comma x2 semicolon. How do you get x1 here? At t equals to t1. So t equals to t1. How do you get here x2? At t equals to t2. So t equals to t2. So fx of x1 comma x2 semicolon t1 comma t2 is equal to what? So already we know the joint distribution function of 2 random variables x and y. So what is the function? fxy of x comma y is equals to what? P of x less than equals to x comma y less than equals to y. If x and y are 2 random variables. So in place of that, if I take 2 random variables x1 and x2, then what is the joint distribution function? Is equals to what? P of x is less than equals to x1 comma and x2 is less than equals to x2. Now what is x1 is nothing but here x of t1. So p of x of t1 is less than equals to here x1. So x1 comma and here x2 is less than equals to x2. What is capital X2? Is nothing but what? X of t2. So x of t2 is less than equals to x2. Okay. And this is called as what? The joint probability. What is this event? So this event is called as what? Joint event. Like A intersection B. X of t1 less than equals to x1 comma x of t2 less than equals to x2. This event is called as what? Joint event. Therefore, this is a second order distribution function of the random variable, of the random process x of t at t equals to t1 and at t equals to t2. Similarly, if you want to calculate, you can calculate the joint distribution function of the third order distribution function also. It means you have to take 3 time instance t1, t2 and t3. The corresponding random variables will becomes x1, x2 and x3. Then the corresponding the joint distribution function is fx of x1 comma x2 comma x3. And how do you get x1? If I fix at t equals to t1, how do you get the random variable x2? If I fix the random process at t equals to t2, how do you get x3? If I fix the random variable, if I fix the random process at t equals to t3, then what do you get here? P of x of t1 less than equals to x1 comma x of t2 less than equals to x2 comma x of t3 less than equals to x3. Like that, I can define the nth order joint distribution functions. Okay. And if I know the joint distribution function, then how can you calculate the joint density function? By taking the differentiation of the distribution function, we'll get the density function. Since it is involving with 2 random variables, I'm taking the second order differentiation. I'm taking what? Second order differentiation. So in the previous case, you're having only one variable. That's why you have taken only first order differentiation. So if you're having two random variables, you have to take the second order differentiation. The second order differentiation of the joint distribution function of the random process at t equals to t1 and t2 is called as what? The second order joint density function of the random process x of t at t equals to t1 and at t equals to t2. Okay. And similarly, I can go for nth order distribution function and density functions also. Now, we have seen the distribution functions and density functions of the random process. So, when can I define the distribution density function for the random process x of t? If and only if I fix the time variable. If time is fixed, then only I can apply the distribution function, density function definitions to the random process, because if I fix the time, then the random process is becoming what? Random variable. It is denoting the random variable. Okay, now, so after finishing the definitions of the distribution function and density function of the random variable, next I have seen what the statistical properties like. I have calculated the mean. I have calculated the mean square value, variance, correlation, covariance, skew, moments, and all those things you can also apply to the random process also. So first you'll see the mean. After that we'll go for the variance formula. So for a random variable x, first you'll see the properties for random variable x. The same thing will apply for random process if I fix the time. So for a random variable x, what is the mean of a random variable x? M is nothing but what? Expectation of x is nothing but what? The mean of the random variable x. So if x is continuous random variable, so if x is a continuous random variable, then what is the formula here? Integration minus 0 to infinity. The expectation of any function is that function. So into the density function fx of x dx. So this is which case? If x is my continuous random variable. Now if x is a discrete random variable, then what is the distribution function? Then what is the mean of the random variable x formula? Sigma I xi into p of x equals to xi. So this is if x is a discrete random variable. Now I'll apply the same concept to the random process also. When can I apply the same concept to the random variable to the random process? If I fix the variable time in the random process. So whatever the mean have calculated for the random variable, the same thing you can also write for random process also. Now the mean of a random process x of t for any t value. So t may be t1, t2, t3 or it may be any value. For any t value, the mean of the random process x of t is equals to what? Integration in case of continuous random process. Okay. Then x of t, expectation of x of t is equals to what? Integration minus infinity x of t into fx of x of t comma t dxt. So I'll write down here. Now write down now. If I fix t equals to t1, then what can the mean of the random process? So in place of t may be here, it is any specific value. It may take t1, t2 and so on. It may take up to n values also. So if I fix the time, the random process at t equals to t1, then x of t is nothing but what? X of t1. So it's nothing but what? Expectation of x1 only, because if I fix the time at t equals to t1, then this random process is becoming what? Random variable. So then what is expectation of x1 is equals to, in place of x, here I am having x1. Then what can I write here? Integration minus infinity x1 into fx of, for a random variable it is called as fx of x. So how I get the random variable x1 from the random process? If I fix the time t equals to t1, then here I can write down here fx of x1 comma t1. How is it called as what? The first order joint first order density function of the random process. Okay, how do I get the random variable x1? If I fix the random process at t equals to t1, I got the random variable x1. Therefore, it is the density function fx of x1. So how do I get here fx of x1? If I fix the random process at t equals to t1. So into what here? Dx. Here what I get here? dx1. Similarly, if you want to calculate the mean of a random process at t equals to t2, then what can I write here? E of x of t2, nothing but expectation of x2 is equals to integration minus f to infinity x2 into fx of x2 comma t2 dx2. Like that, I can calculate the mean value of the random process at any time instant. Now, we have taken the definition of the stationary random process. What is a stationary random process? Whose statistical properties does not change with time. Therefore, if x of t is a stationary random process, then what is the mean of the random process? It is a constant. The mean will not depend upon the variable t. We will get a constant value. For which case, if a random process x of t is a stationary random process. So, in the similar manner, I can calculate the variance of a random process at a fixed time. So, what is the variance of a random variable? Sigma x square. So, if x is a random variable, then how can I define the variance of the random variable x is equals to what? Expectation of x minus x bar whole square. In place of x bar, I can represent with m. What is m? Is nothing but the mean of the random variable. Or else, if I simplify this, what I get here? E of x square minus m square. Now, the same concept of the random variance, I can also apply to the random process also. So, what is the variance of the random process? Here, you have a random variable x. Here also, in place of the random variable, here it is a random process at a particular time instant t. And what is the variance of the random process? X of t is equals to expectation of x of t minus mx of t. What is mx of t? Is called as the mean of the random process x of t at a particular time t. Okay, so like that, whatever the concept I have applied to the random variable, the same concept I can also apply to the random process also. Now, all these things I will explain with an example how to calculate the mean variance of a random process and at a particular instance. Here is a question like, a random process x of t is determined by tossing two dice. A random process x of t is determined by tossing two dice to determine which of the following sinusoidal to pick up. So, what is random process x of t is equals to x1 of t. What is my x1 of t? Nothing but sin t if the sum is 3 or 7. And what is x2 of t equals to cos 2t if the sum is 2 or 12. And x3 of t is equals to sin 2t or else. It means other than the sum 3, 7, 2 or 12, for remaining sums, I have to assign the time function sin 2t. So what I have to calculate here? Find the mean and variance of the random process x of t. And also you have to calculate the mean and variance of the random process at t equals to t4. The mean and variance of the random process x of t at t equals to pi by 4. And similarly, the mean and variance of the random process x of t at t equals to pi by 2. So, what is the random process? I told you that it is a function of both the sample space elements as well as the time. If I take here x of t, what is sum 3 or 7? What is my experiment here? Tossing two dice. Then what is sample space consists of 36 elements. So you may get 1, 1, 1, 2, 1, 3, 1, 4. First die is 1, second die is 1. First die is 1, second die is like that. I'll get 36 possibilities. It means it is a sample space elements. Is it right? So the random process is depending upon what? The sample space elements as well as it is depending upon the variable t. Therefore, it is called as what? Random process. RS, what is the definition of the random process I have given? For each outcome of the experiment, if I assign a time function, it is called as what? Time function. And the combination of all these time functions is called as what? A random process x of t. So now I have to calculate the mean So what is the mean of the random process? E of x of t is equals to, and how to take which type of random process. Here it is. So if I take here, what is experiment? Tossing the two dice. So if I toss the dice for two dice, then the sample space consists of 6 square, that equals to total it consists of 36 elements. What are the 36 elements is equals to, first die is 1, second die is 1, first die is 1, second die 2. So and so on like this. And similarly, first die is 6 and second die shows 1 and so on, 6 comma 6. So totally how many elements I'm going to get? 36 elements. These are all the possibilities. That is the sample space when I throw two dice. Okay. Now, if I see the sample space, how many number of elements having 36 elements. It means the elements are countable and finite. Therefore, what type of random process here? It is a discrete. It is a discrete random process. The type of random process here S is discrete because what is the reason? The elements of the sample space are countable and finite. Therefore, S is discrete. Whatever the time, they have not given fixed time here. Therefore, time is continuous. The type of random process is what? Discrete random process. If S is discrete and T is continuous, then it is called as what? A discrete random. If T is continuous, I'll call it as what? Process. If T is discrete, I'll call it as sequence. Since T is continuous, it is called as what? Random process. Okay. Now, for discrete random process, how do you calculate the variance? You have to take the sigma. Instead of integration, you have to take the sigma. So, sigma I x of, okay. So, xi of t into p of x of ti is equals to xi of t. So, this is a expectation or the mean. Here nothing but what? The mean. So, the mean of the random process for any time t. So, like this I can define here. Okay. This is a formula. Why I have used only sigma? Because here my S is discrete. Since S is discrete, I have to go for discrete. It is a T is continuous. It is called as what? Discrete random process. So for discrete, for discrete random variable, what is a formula to calculate the mean? Instead of integration, I will take the summation. So sigma I xi of t, p of x of ti at xi of t. Okay. Now, so we first taking the first case. What is the first case is sum is 3 or 7. So when I'll get sum is equals to 3 or 7. So sum equals to 3 or 7. What are the possibilities for this? First die 1, second die 2. First die 2, second die is 1. And to get the sum is 7, first die is 1, second die is 6. And first die is 6 and second die is 1. Next, first die shows 2, second die is 5. And first die shows 5, second die shows 2. And the first die shows 3, second die is 4. The first die 4, the second die is 3. Totally, how many elements consist of? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 possibilities. And total, how many possibilities I'm having here? 36 possibilities. Because the number of sample space elements are 36. Then, what is the probability of the random process at t equals to t1? See here. Okay. So, x1 of t is equals to what? What is the p of x1 of t? It's nothing but what? P of x1 of t. Okay. When I get the sum is 3 or 7. So, when I get the sum is 3 or 7, what is the probability? I am getting only 8 possibilities out of 36. Then what is the probability here? 8 by 36. So therefore, what is P of x1 of t? Nothing but 8 by 36. This is also called as what? P of x of t. Okay. At x1 of t. Like this also can represent. And what is the second case? When sum is, so what they are given? The sum is 2 or 12. So when the sum is 2 or 12, then what is the probability of, okay, the random process x2 of t? Nothing but what? P of x2 of t at sum is 2 or 12. So when I get the sum is 2 or 12, the possibilities when both dash shows 1, when both dash shows 6. So totally 1, 2 possibilities out of 36. Then what is probability is equals to 2 by 36. And next second case, what they are given? Third case, they have given as when the sum is otherwise. So when the sum is otherwise. So what is the probability then? The sum is other than 3, 7, 2 or 12. Nothing but what you calculate here? The probability of the random process at x of t is equals to x3 of t. Nothing but what? The probability of the random process x of t is equals to what? x3 of t is equals to what? If I want this, what is the total probability? 1. So 1 minus, what is the probability that getting the sum is 3 or 7 is 8 by 36. And what is the probability that the sum is 2 by 36? 2 or 12 is 2 by 36. And what is the probability other than this 3, 7, 2 or 12 means total probability minus 1 minus sum of these two probabilities is equal to 36 and here 36 minus 10. So 16 by 36. Okay. Now what I have to calculate? I have to calculate the mean of the random process. Then what is E of x of t is equals to sigma I equals to 1 to 3. Because here I am having here what? x1 of t, x2 of t, x3 of t. Therefore I am taking here I equals to 1 to 3. Okay. So write down here 1 to 3 xi of t into p of x of t at xi of t. Now, if I substitute here 1, so x1 of t into p of x of t at x1 of t plus x2 of t into p of x of t at x2 of t plus x3 of t into p of x of t equals to x3 of t. Then equals to what is x1 of t they have given? So in the problem they have given x1 of t is sin t. And what is the probability at x1 of t equals 8 by 36. Therefore what do you get here? Here it is what is the x1 of t equals to sin t. Sin t into 8 by 36 plus x2 of t. What is x2 of t they are given in the problem? Cos 2t. And what is the probability at this? Is equals to 2 by 36. So what do you get here? Cos 2t into 2 by 36 plus x3 of t. So x3 of t into p of x of t is equals to x3 of t. So what is x3 of t here? Sin 2t. And what is the probability that x of t equals x3 of t? Probability I calculate 16 by 36. So sin 2t into 16 by 36. So this is what the mean of the random process x of t. If I observe the mean of the random process, it is depending upon time. It is depending upon time. Therefore, what is the type of random process? It is random process said to be what? Non-stationary. Because the statistical properties, the mean is changing with respect to the time. That's why the statistical properties are changing with respect to time. If t is changed, the mean is also changing. Is it right? It means the statistical properties in the random process are also changing. If the statistical properties are changing with respect to time, then that type of random process is called as what? Non-stationary random process. So like that, you can calculate the mean of the random process x of t. Okay, next what you have to calculate? You have to calculate the variance. So this is the mean of the random process. So this is the first bit. Okay, and what you have to calculate? You have to calculate the variance of the random process. So variance of the random process. So what is the variance of the random process? E of x of t minus E of x of t whole square. For a random variable, what is the formula? E of x minus E of x whole square, or else E of x minus x bar square. Okay. So let us say this is nothing but x bar here. Okay. Then if I simplify, what I get here? E of x square minus x bar square. And similarly, if I simplify this, what I get here? E of x square of t minus, okay, minus x bar square. What is my x bar here? E of x of t. So minus E of x of t whole square. So in order to calculate the variance, already have calculated the mean. So this is what? Mean value, and this is a mean square of the random process. Already I have calculated the mean. If I calculate the mean square value, then I can calculate the variance. So first I will find out the mean square value of the random process. Then what is the mean square of the random process? E of x square of t is equals to what? Sigma I equals to 1 to 3. If I have here x of t, it is xi of t. In place of x of t here, x square of t, then what I get here? Xi square of t into what? P of x of t at x of t equals to xi of t. It implies if I equals to 1, what I get here? X1 square of t into P of x of t at x1 of t plus if I equals to 2, x2 square of t into P of x of t at x2 of t plus if I equals to 3, substitute here, x3 square of t into P of x of t at x3 of t. Now what is x1 of t in the given problem? Sin t. Then what is x1 square of t? Sin square t. So it is sin square t. Now what is the corresponding probability of the random process at x1 of t is 8 by 36. So 8 by 36 plus x square of t. What is x2 of t is cos 2t. Then square is nothing but cos square of 2t into 2 by 36 plus sin square 2t into 16 by 36. Then what is the variance? Sigma x square is equals to E of x square of t minus E of x of t whole square. Then what is E of x square of t? I have calculated here sin square t into 8 by 36. So sin square t into 8 by 36 plus cos square 2t into 2 by 36. So cos square 2t into 2 by 36 plus sin square 2t into 16 by 36. So 16 by 36. So this is nothing but what? E of x square of t minus what is the mean of the random process I have calculated is sin t into 8 by 36 plus cos 2t into 2 by 36 plus sin 2t into 16 by 36 and then whole square. So this is the variance of the random process. So I have calculated the mean and I have calculated the variance. And second bit, what I have to calculate? How to calculate the mean and variance of the random process at t equals to pi by 4. So at t equals to what? Pi by 4. I have to calculate the mean and variance of the random process at t equals to pi by 4. And what is the mean of the random process? I know. So in place of t, what I have substitute here? Pi by 4. Then what is x of t of pi by 4? So what is the mean formula here? Sin t into 8 by 36 cos 2t into 2 by 36 plus sin 2t into 16 by 36. So in place of t, what I substitute here? Pi by 4. Then here x of, so in place of t, I am having here what? Pi by 4. Then what is this value? Sin pi by 4 into 8 by 36. Wherever t is there, the mean value substitute. So cos 2 into pi by 4 into 2 by 36 cos 2 pi by 4 here. This is sin pi by 4 plus sin 2 pi by 4 into 16 by 36. So if I simplify this value, then I'm going to get the answer here 0.8793. So what is the value I'm going to get here? 0.8793. So this is the mean. And what is the variance? How do you calculate the variance? Sigma x square. So in this equation 1, so substitute t equals to pi by 4. Then you'll get the variance of the random process at t equals to pi by 4. So if I substitute, what I get here? Sine square t in place of t pi by 4. So into what? 8 by 36 plus cos square 2 into pi by 4. So into what I'm having here? 2 by 36 plus sine square 2 into pi by 4 into 16 by 36 minus x of t whole square. Already have calculated this value here, the mean. So this 0.8793 square. So if I simplify this, I'm going to get the answer 0.0602. So what is the answer I'm going to get here? 0.0602. So this is a variance at t equals to pi by 4. Similarly, I can calculate the mean and variance at t equals to pi by 2 also. So what I do here? This is previously calculated pi by 4. So in place of pi by 4, what you have to do? You have to substitute pi by 2. Then what is the mean here? X of t, in place of t, it is pi by 2 is equals to what? What is the mean here? Sin t into 8 by 36 plus. This is the mean. So sin, in place of t, substitute pi by 2. So what do you get here? Sin pi by 2 into 8 by 36 plus cos 2 pi by 2 into cos 2 pi by 2 into 2 by 36 plus sin 2 pi by 2 into 16 by 36. So if I simplify this, so I'm going to get the answer is 1 by 6. What is the answer I'm going to get here? 1 by 6. And similarly, I can calculate the variance at t equals to pi by 2. At t equals to pi by 2. Then what is the variance I'm going to get here? It is, so the answer is here, it is 1 by 4. So in this equation, so replace t by pi by 2 in this equation, then you are going to get the variance at t equals to pi by 2. So the value is 1 by 2 is the answer. 1 by 2 or 1 by 4. So 1 by 4 is the answer here. So therefore here it is 1 by 4. So like that, I can calculate the mean and variance of any random process x of t. Okay. So till now I have seen the mean and variance is one of the statistical property. And next I am going for correlation. So what is the correlation of two random variables x1, x2? Already we have seen in the concept in the random variables is equals to what? E of x1 into x2. So expectation of x1 into x2 is called as what? Correlation of the random variables x1, x2. And what is autocorrelation? It means I'll take the same random process x of t. At the random process, I'm taking a 2 instance at t equals to t1. Then the random process, nothing but random variable x1. At t equals to t2, then the random process is the random variable x2. And the correlation of these two random variables is called as what? Autocorrelation of a random process x of t. So how it is defined? So here E of x1 into x2. What is x1? X of t1. And what is x2? Here x of t2. In case of continuous random variable, how can I calculate the expectation? I'll take the integration. So integration of the function into the joint density function. So like that, I can calculate the autocorrelation function. And these are the some of the properties of the autocorrelation function. And first order stationary. What do you mean first order stationary? What is stationary? The statistical properties do not change with time. It is called as what? Stationary random process. Then what is the first order stationary? If its first order distribution function and density function does not change with time, it is called as what? First order stationary random process. Okay. And what is the second order density function stationary random process? What is if its second order distribution function and density function does not change with the shift in time. It means here at T1, the T1 has been shifted to the T1 plus tau and T2 has been shifted to the T2 plus tau. Okay, even though it is shifted, what about the distribution function is not changing. So you are getting the same value, and similarly the density function also. So because of the change in or shift in time, the distribution function and density function, the second order distribution function density function does not vary with time. It is called as what? Second order stationary random process. Okay, and the autocorrelation function of the second order density function, so does not change with time. It's nothing but you'll get a constant value. It will not depend upon what t. So Rx of here, what is that? It is a autocorrelation with random process x of t at t equals to t and t equals to t plus tau. Okay, but it is depending upon both t and the constant variable tau. For a stationary random process, if it is stationary, if it is a stationary second order stationary random process, if you observe this, it is depending only upon the constant tau. It is not depending upon the time. Therefore, with the second order stationary random process, the autocorrelation function is not depending upon the time. You get a constant value. And the statistical independence. So, what is the statistical independence? We have seen the independent two variables. For example, if x1 and x2 are two random variables, then if these two random variables are statistically independent, when can you say that? If the joint distribution, the joint density function of these two random variables is equal to the product of their marginal distribution functions. So fx of x2 of x2. If x1, x2 are two random variables, then these two random variables are said to be statistically independent if their joint density function is equal to the product of their joint density functions. Product of their marginal density functions. The same concept I'll apply to the random process also. So in place of x1, x2 or in place of x, y, the random variables if I take, then what is fxy of x comma y is equals to fx of x into fy of y. Then these two random variables are said to be statistically independent. Now in place of x and y, I am taking two random processes x of t and y of t. And the random variables associated with this random process x of t are x1, x2 and so on xn. And the random variables associated with the random process y of t. How do you get this? The random variables in the random process by fixing the time interval. So y of t1 and so on, y of t1 dash, t2 dash and so on, tn dash. Then, so how many random variables you are getting here? x1, x2 and so on, xn, n random variables. And similarly for this, you are getting n random variables, y1 and so on, yn. Then the joint density function of these n random variables has been represented by what? fx of x1, x2 and so on, xn. How do you get x1? If I fix the random process at t equals t1, I am getting x1. How do you get x2? If I fix the random process at t equals t2, I am getting x2 and so on. And similarly, the random process y of t, what is the joint density function? The random process y of t. So fy of y1, y2 and so on, yn. How do you get y1? If I fix the random process y of t at t equals to t1 dash, I am getting y1. And how do you get the random variable y2? If I fix the random process y of t at t equals t2 dash, I am getting the random variable y2. Then these two random process x of t and y of t are independent, statistically independent if their joint density function is equal to the product of their individual joint density functions. There is nothing but fxy of x1, x2 and so on xn. Okay, comma y1, y2 and so on yn of t1 dash, t2 dash. Here in place of x, y, here I am having this. So in place of x, here x1 to xn. In place of y, I have here y1 to yn. In place of x, x1 to xn. In place of y, y1 to yn. Is equal to what? Product of their individual joint density functions of x of t and y of t. So this is the condition for to two random process to be statistically independent. So in today's lecture, we have seen the concept of stationary random process, and then we have seen the concept of statistical independence of two random process. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.